Okay, today we're talking about volatile guaiacols and other markers of smoke impact in grapes and wines. So what we as a lab can do to help you assess the impact of smoke in grapes and in wines. The first part will be a recap of the various markers that have been proposed so far in grapes and in wines. And the second part is the results of a study following the fires in Lake County in 2018. So volatile markers of smoke impact, they're coming from the degradation of lignin. So lignin is one of the main components of wood and straw. That's a model of lignin here. That's a big polymer, so a big molecule made of several building blocks. And when it is exposed to intense heat, before it burns, it breaks down, giving smaller molecules that are small enough to get airborne. So they will give to smoke its characteristic odor. So when lignin breaks where the arrows are here, you're getting guaiacol. When it breaks here, you're getting 4-methyl guaiacol. That's the main two markers of smoke impact in grapes and in wine. They've been proposed for about 12 years now. Other proposed markers are the cresols. 3 forms of cresols exist. Phenol itself, so all these molecules are volatile phenols, and the most simple of them, phenol itself, is proposed as a marker also of smoke impact. And 2 more molecules have been proposed, cyrangol and 4-methylcyrangol, also related, also volatile phenols. When grapes are exposed to smoke, grapes tend to absorb smoke volatile compounds, but next thing they do is that they tend to bind them to sugars. That's not your basic glucose and fructose, sugars with more exotic names like gentobiose, retinose, and basically each volatile phenols can be bound to, in theory, a variety of sugars, giving a complex mixture of compounds. So that's the main compounds that have been proposed by the AWRI research team in 2013. At this point, the AWRI analytical services offer testing routinely for 6 of these markers that they consider the main ones. Why do grapes do that? That's probably a defense mechanism. Smoke compounds have some toxicity. That's why we use smoke to preserve fish and meat. So when live grape cells are exposed to smoke, basically the cells defend themselves by binding these compounds to sugars. It makes them very water soluble, meaning that they can be transported within the cell and they can be dumped in the vacuole, where they won't interfere with vital metabolism. In 2018, just a little bit north of the Napa Valley, we experienced the largest wildfire in California history. So on this picture here, you see the dark blue spot is that's Clear Lake. That's the largest lake entirely in California, and the fires around it. And that was next to the area where the Lake County grapes are grown. So when this happened, Lake County growers were interested in finding tests to assess the impact of smoke in their grapes and wines. Later on, when they looked for information, they ended up finding confusing and conflicting information, and they decided to put together a group. So they went to the UC Cooperative Extension, to the AWRI and its commercial services, and to us at ETS. And after a few conference calls, we ended up with a study design as follows. So basically, Glenn McGurty from UC Extension selected 13 different vineyards, all Cabernet Sauvignon to make things simple. And he sampled clusters from these vineyards and split the samples and sent us berry samples for direct analysis of volatile guaiacols. That's the test that we've been doing for about 12 years now to give an idea of the smoke impact in grapes. And then the rest was micro-fermented, so fermented in a small scale, and that gave wines that were tasted. And also samples were sent to the AWRI for analysis of volatile markers and glycosylated markers. And also we worked on them with a volatile panel and glycosylated markers that we could analyze. At the time it was still a method under development. Main findings of this study are presented in Wine Business Monthly, the January issue by Glenn McGurty. And let's review first the key findings of that study. Glenn is saying that the concentrations of guaiacol and 4-methyl guaiacol, so free forms, in fruit, so in grapes, ended up to be highly correlating to those in wines, in the microferments. And also that the sensory analysis of the wine was closely correlated to these results, the results of the sensory evaluations. So what does it mean? It means that if we look at free guaiacol levels in berries, that's the x-axis here, versus what ended up in microferments, first, there's a very strong correlation. So basically, the berries guaiacol was predictive of what ended up in the microferments. Typically, we see 3 to 5 times more guaiacol in microferments than berries. This is attributed to the partial hydrolysis of glycosylated forms. In that case, it was about that. It was about 4 times if we exclude the outlier in the end, the sample with sky-high results. So multiplier here, so 2.3. But if we exclude this multiplier, that would be pretty much false. The smoke characters in the microferments were clearly correlated with the guaiacol levels in the microferments, and also, consequently, to the levels that we found in the fresh berries. So more or less, this confirmed the basic interpretation guidelines that we've been giving for almost 10 years for free guaiacol in berries. So basically, the higher the level, the higher the risk of smoke characters showing up in wine. Now, I'm going to show you what we've been using as guidelines so far for interpretation of our results for grapes and for wines and microferments. This is based on our experience so far. There's no guarantee that it will apply to every wildfire or any fire in the future. It's based on what we've seen since 2008, but still every fire is different. Timing is of exposure to smoke is different, duration, the age of the smoke, etc. So these guidelines may not apply to future events. Also, any guideline that has to do with sensory, of course, you have to realize that there are huge variations in sensitivity with individuals. Some are very sensitive to smoke, some are very sensitive to the odor but not the aftertaste, some extremely sensitive to the aftertaste, and that's something that needs to be recognized also. We give results down to 0.5 microgram per kilogram of guaiacol in grapes. And below that level, we don't have a clear indication that really there was a measurable absorption of smoke compounds by grapes. At that level or below that level, we consider that the risk of smoke characters showing up in wine are low to very low. And then when it increases, the risk increases. Between 0.5 and 1 ppb in most grapes, except Syrah, we consider that it's probably not natural anymore. What we're seeing is the result of absorption of smoke compounds. And the risk of smoke characters noticeable in wine starts to increase. Between 0.5 and 1, it's still moderate still, but significant. Between 1 and 2, it's not magic numbers, but let's say between 1 and 2, the risk becomes high. Past 2 ppb or microgram per kilogram, very high. Actually, to our experience, usually you can expect to get some smoke characters in wines past that point, unfortunately. Okay, so now in wines themselves, so it's a different unit, microgram per liter, different scale. Again, these guidelines are based on our experience so far since 2008. No guarantee that they will not change in the future. We are learning every year, and every year is going to be different. Maybe it's going to challenge these guidelines. Again, every fire is different. The timing of exposure to smoke can be different. Also, any guidelines that have to do with sensory, you have to recognize differences between individuals, some extremely sensitive to smoke characters, some much less sensitive. We give results down to 1 microgram per liter, and between 1 and 2, we believe that the smoke impact in wines is unlikely to be noticeable, especially in red wines. That's normal levels. In white, we see sometimes less than 1, but between 1 and 2, still unlikely to have any smoke impact noticeable. Around 3 ppb or so, the positive identification of smoke characters become more likely. Past 4 really likely, and past 6 most likely. Usually it's quite easily noticed. So let's review the pros and cons of 2 techniques or tools that you have to assess the smoke impact in grapes before harvest, pre-harvest. So you can collect the grape samples, send them to the lab for analysis, or you can make microferments. The big advantage of grape samples is that you have a sample that is ready for analysis right away. With microferments, you have to wait more than 1 week. With grapes, the sensory evaluation, by the way, is not very useful. You can smell some smoke sometimes in grapes, usually when the exposure to smoke happened relatively close to harvest. When it happens before, by the time you harvest, you won't smell anything, but the risk is still present. With wines, a big advantage is that you end up with wines that you can taste, so you can get a better idea of what you're facing really in commercial wines. Still, it's not that easy. You need individuals differ in their sensitivity to smoke, so it's a good advice to try to identify individuals that are sensitive to smoke. Analysis turnaround time, same thing. It doesn't matter to us if we get grapes or wine samples at the lab. Grapes take a little bit longer to process, but not by much. Now, what about the prediction power of these tools? Well, a limitation of grapes is that what we measure in grapes, you saw that, is lower usually than what will end up in wines, and we never know exactly what the multiplier will be between grapes and wines. That's a limitation. With red wines, if you do microferments, you have a more direct prediction, but again delayed. With white wines, the problem is that the smoke compounds you will extract completely depend on how you get your juice sample. The more skin contact, the more smoke compounds are extracted. So maybe for microferments, it's a good advice to ferment with skins for a worst case scenario protocol, basically. Okay, so that was a recap of the pros and cons of the two tools that you have before harvest to get an idea of the smoke impact when you know that your grapes have been exposed to smoke. Still be careful. One of the key observations of Glenn was that below 6 micrograms per liter, more or less for guaiacol, it was difficult for testers to identify consistently smoke characters in the microfermented wines. Basically, the wines with the higher levels here were clearly identified, the ones below that not as consistently. And that can be a problem because in commercial wines, to our experience, that's levels that can cause problems. So now, new insights. As Glenn says, as the concentrations of guaiacol increase, so do all other compounds. So let's dig a little bit deeper and see what happens with glycosylated markers and free markers. So when you want to see if two compounds are correlated with each other, you prepare a correlation chart like this one. So on the x-axis here, that's the concentration of guaiacol in microferments. On the y-axis, the concentration of one of the cresols, orthocresol. And you can see that the correlation is extremely tight here, with almost 1 as a squared correlation coefficient. And this means really that one compound and the other are very closely correlated. So correlation charts like this one are very useful to compare two compounds to each other. Problem is we had 30 compounds we wanted to look at total, so 32 times 32, that's more than 1000. So when you have to look at so many compounds, what you do is to generate a correlation matrix where you put just a correlation coefficient between two compounds. So on the first row you see volatile markers, on the first column you see the same markers, and if you look at the diagonal you see only ones. It's because you're comparing each compound to itself. Okay, so obviously the comparison is perfect, or the correlation is perfect. When you look at other compounds, so if you look at the first column, that's how guaiacol is correlated with other compounds here, that's 3 phenols. And you can add colors to that map and turn it into a heat map, so that right away you have a sense of what is correlated with what and what is not. And obviously here you see shades of greens and yellow that are dominant. That's for compounds that are correlated to each other. And there is some orange or red where there's a very poor correlation. That's with syringol and everything else. And actually methylsyringol, that's the AWRI results here. Methylsyringol was below the reportable level. It was not even reportable. So that could be a surprise, but it was confirmed by our results too. So we looked a little bit lower for methylsyringol, but basically same results. Syringol and methylsyringol do not appear correlated with the other compounds. Phenol itself is well correlated. So basically that's a confirmation that most of the markers proposed, the 3 markers, are valid, but with the exception, in that case, of the syringols. So now let's make it more complicated. Let's look also at glycosylated markers. And the top left of the table here is something that you saw 2 slides ago. That's the correlations between volatile markers and the rest is between volatile markers and glycosylated markers, and the bottom right, glycosylated compounds with themselves. So mostly shades of green, again, even yellow, but even if you look at the yellow, it's mostly higher than 0.9, which is still an extremely good correlation coefficient. So we have a confirmation here that the glycosylated markers seem relevant. By the way, they are relevant in, at least in that case, in this fire that happened in California, but the volatile syringles didn't seem to be adequate markers in that case. We confirmed that, and so that's something difficult to look at because there's so many compounds here, and I didn't put all of them. Basically, if you look at the column on the left, that's the listing of all the compounds. What is orange is the glycosylated markers offered by the AWRI in routine, and you can see that the colors for these markers with basically everything else is green or dark green, so very good correlations with the volatile markers and the rest of the glycosylated markers that are normally reported by AWRI, and a few other markers, 3 more, and again, with the exception maybe of the volatile syringles not correlated with anything, and some methyl syringol also glycosylated forms that don't seem to be correlated with anything else. But the take-home message here is that basically the 3 volatile compounds typically proposed and glycosylated markers appeared to be valid, and a few additional glycosylated markers could be added to the mix. But the surprising observation here was that volatile syringles did not appear at all related to smoke impact in that case. So we can speculate, are they absent from the fire in California wildfires? Quite probably not. Are they not absorbed by grapes? Probably not. And by the way, one class of glycosylated syringles, the gentiobioside, was very clearly related to smoke impact and very responsive to the exposure to smoke, which means that syringles were present in the smoke. They were absorbed by grapes, but they were efficiently, very efficiently glycosylated. So what we're probably seeing here is the result of first a specificity of glycosylation, a preferential binding. By the way, the cresols, guaiacols, and phenol seemed to bind preferentially to rutinos, and the syringles to one sugar, gentiobiose. And that contradicts a little bit what we were thinking after that publication in 2017. That's a publication that showed that the glucosyl transferase, so the enzyme that normally binds resveratrol, so that's a natural grape phenol, and this is normally bound to glucose. Well, this enzyme is not very specific and can bind also guaiacol. It's like it confuses guaiacol with resveratrol and does the same thing, binds it to glucose. So the thinking was, okay, maybe all these enzymes involved in glycosylation of smoke volatiles are not very specific and bind a little bit everything to any sugar pretty much, but it is not that simple. So again, so specificity, there is clearly some specificity of glycosylation. Efficiency of glycosylation seems variable too. With guaiacol, enough volatile compounds remained in grapes so that they gave, and also cresols and phenols, so that they gave a good estimation of the risk of smoke impact, of the exposure to smoke. With syringles, it looks like the glycosylation was so efficient that there wasn't basically any volatile serangles to detect for them to be useful markers at all. The stability of glycosylated phenols seems to be variable. Glycosylated guaiacols were partially hydrolyzed during fermentation. As you see, what we could measure as free forms between grapes and wines was clearly correlated, but there was a multiplier of about 4 for most samples. So, partial hydrolysis. Glycosylated serangles seemed to resist this hydrolysis to the point that in grapes and in wines also, the volatile serangles were not useful markers either. So at this point, the volatile guaiacols clearly are relevant and are a good tool for risk assessment before harvest in both grapes and microferments. A good confirmation is with commercial wines to do a measurement at the end of primary fermentation when the hydrolysis of the glycosylated forms slows down and basically virtually comes to a halt. What matters really in grapes and in wines is to have very low minimum reportable levels. You need to go down to 0.5 ppb to our experience in grapes and 1 ppb or microgram per liter in wines or microferments. The rest of the volatile phenols proposed are confirmed to be very useful markers. Apparently, in that case, at least, the serangles were not, and it wasn't totally a surprise to us. We've noticed that in previous fire events, that the serangles didn't seem good indicators of smoke impact, of exposure to smoke, at least with these fire events. At least they're useful because they're also given by toasted oak, and we could use them as to confirm the interference of toasted oak when you're looking at results with commercial wines or wines for which we don't know if they have been in contact with toasted oak or not. Glycosylated phenols. So the 6 AWRI markers clearly appeared relevant in California too, at least for this fire event. A few other may be useful. The big advantage of glycosylated phenols is that they are not given by toasted oak, so they will be essential to assess oaked wines. With one caveat, it's that we need to have a good database so that we know what are normal native levels to expect in grapes and wines not exposed to smoke for the interpretations to be valid. Okay, because even in non-smoked in grapes, from non-smoke in wines, from non-exposed grapes, we can detect these compounds in most cases. A big thank you to these two people here, Deborah Sommerfield and Peter Molnar from the Lake County Wine Grape Growers Commission. Really, they spearheaded this project and made these collaborations possible. So thanks also to all the Lake County growers, to Glenn McCourty and his collaborators at the UC Cooperative Extension, Dr. Mark Kirstig, Eric Wilkes, and Marcus Herderich at the AWRI, and our own Dr. Azim Azam and Darren Gulick, who did the analysis of extended volatile markers and glycosylated markers. Thank you for your attention. If you have questions, feel free to contact me directly at ETS. That's my direct line here, and that's my email. Thank you for listening.